In the previous set of videos, you learned about two different data structures, which is sets and maps, and we discussed the ADTs of sets and maps in C++ is actually implemented using two different mechanisms. The first one we discussed already, which is the standard map or standard set, which are backed up by tree-based data structures such as red-black trees. And the other one was unordered maps or sets, which are essentially backed up by something called hash tables, which we are going to discuss today. So essentially, we are going to actually close this topic of not ordered data structures, which is sets, maps, and tables, hash tables. Now, one thing to note here is that when we were specifically naming these data structures, sets, tables, and maps, we never actually paid attention to not ordered, which is the data that was being stored in the other data structures were actually ordered, which means there was some sort of a comparative metric that would allow us to order the data. But let's say if we have different types of data that cannot be actually compared, which is let's say if you have files, large files, how do we compare which one is which one should proceed in which direction? Which is let's say when we talk about different forms of trees, we knew that let's say if all of those trees followed the BST properties, which is if we go towards the left, it should be lesser. If we go towards the right, it should be greater. But there might be some form of data that does not actually satisfy this constraint that it can be compared. So that's why we actually need not ordered data structures, which are agnostic to the type of data. So that's what we are going to talk about today, which is hash tables, and we'll discuss why they are needed along with the properties, how they are implemented, and what sort of problems do we see. And finally, we'll discuss the performance and end the lecture right there. So let's discuss why do we need hash tables in the first place. So when we implemented maps and sets, which were based on trees, which were backed up by red, black trees or any form of balanced trees, there were two big problems that we were dealing with. The first one is if the data itself is uncomparable, which is it has some sort of data that cannot be compared with each other. Let's say if you have two files, or let's say if you have two objects, you create two classes and you do not overload the comparable method, then how do we actually support this data which has a user defined data type into our data structures? So that's why we'll try to create a data structure that's agnostic to that. And the second one was the common operations in tree-based maps or sets. Let's say if I try to insert an element into my set, which is backed up by a tree, essentially you will start from the top and keep going left or right depending on where it needs to be inserted, and you will append it just like a regular BST or a red black tree. So in that case, insertions and searches both required log n time. But the question to ask here is, can we do better than this? Is it actually possible? And that's the whole purpose of today's lecture, which is we are going to see how can we improve on that, which is can we actually change O log n is absolutely great. Let's say if I have a billion entries, okay, and if I have a billion entries into my set or a map, and if I were to look a particular element log base 2 of this big number is going to be still a very small number, maybe 30 or 100, somewhere around that mark. So in the next video, we are going to see how although this is really fast, can we actually execute this even faster, which is can we get something like constant time or complexity for lookups or for inserting new values. And that's the whole purpose of hash tables. So in the next video, we are going to discuss how that's actually implemented. Thanks.